For that way, if you miss anything or if you have to leave early, you can always look at the recording. So let me start sharing my screen. So today we're going to be kind of going over a big topic. So today's topic is sampling distribution. So for sampling distribution, it's kind of a little bit of the O, but we're kind of going to switch up some of the formula. So what I mean about that is we have to adjust our formula because before we're always finding the probability of one random event occurring. But now what we're gonna do, we're gonna start focusing on when we have a random event, but now we have n many random events. So instead of just saying we have a simple random sample of just one person or one object, what we're gonna do, we're gonna just say we have a random sample of n many people. So that's what the sampling distribution is going to entail about. So kind of like the idea of the sampling distribution is that you have a population, and what we do, we continually randomly select a certain amount of people from that population. And what we do from that population, we make a new population. So if you go to illustrating sampling distribution, this is kind of the steps. So step number one, you want to obtain a simple random sample. So say we say a simple random sample of 30. And then what you want to do, you want to compute the sample mean of that. So we create a sample mean. And let's say we get a sample mean of 10. But this sample mean is now going to be one data point. And what we're going to do, we're going to keep on repeating step 1 and 2 until we essentially sample the entire population. The kind of thing about the population having a million people. And what we do, we take random sample of 30 people every time until we pretty much get all of the people in that population. And using that new data set, we're going to create a new population. So that's kind of hard to visualize. So luckily I have this applet, and hopefully from this applet it should kind of demonstrate that. So let me do this. All right. So here's our population distribution. So if you look at our population distribution, what type of distribution does it have? Is it skewed to the left, skewed to the right, or is it symmetric? And if you want, you put in the chat if you don't want to speak up.
Skewed to the right.
Yeah, skewed to the right. So what we're going to go ahead and do, we're going to start sampling from this distribution. And let's see what's going to happen. So let me see. All right. So we're going to take a sample size. So let's do a sample size of 30. So what we're going to do, we're going to take a sample size of 30 here. So right now, this is the setting that I have it on. So we're going to take one sample. So that means we're going to take one sample of 30. Once we get the 30 sample, what we're going to do, we're going to take the average of those 30 samples. And that's going to be our one data point. So let's go draw sample. All right. So let's kind of go through the process. So here's our population, and we randomly select 30 from this population. These are the 30 that I selected. So if you look at the 30 that I selected, the mean of those 30 was 7.775. My standard deviation was 1.294. and my n is 30. So the only thing I'm going to get from this is my mean. And that's going to be my singular point. So if you look at that blue dot, that's one of my points. So now what we're going to go ahead and do, we're going to do the process all over again. So we're going to say, draw another sample. So here's my population. From my population, I'm getting a sample of 30, and I get a new mean. My new mean is 7.983. So now we have 2 data points. So just to kind of speed this up, instead of just saying do this one at a time, I'm going to tell it to do it 100 at a time. So we're going to tell it to do this 98 times more. So let's go ahead and do this. All right. So if you look at my original distribution, we said the distribution was what? Skewed to the left, skewed to the right, or symmetric?
Skewed to the right.
Yeah, so we said it was skewed to the right. But let's see what happened to our distribution that we were randomly selecting. So if you look at the distribution that we were randomly selecting, what type of distribution does that one have?
Symmetrical.
Yeah, so it'll be symmetrical, or you could also say a normal distribution. So that's something that we're also going to learn today is something called the central limit theorem. So the central limit theorem said if we start randomly selecting n many people or n many objects, our new distribution that we're randomly selecting for is going to have a normal distribution or symmetrical. And this is what this is kind of showing, it's symmetrical. So that's going based off of the central limit theorem. So I also kind of want you to notice, if I look at this one, at the first one, where is the lowest number that we get? And you can just guess, like, no shame in guessing. So what's the lowest number in this histogram? Yeah, so the lowest number should be somewhere like at 5. What about what's the highest number that we have? Yeah, so if you look at it, go from 5 all the way to 20. But let's see what happened with my new distribution. In my new distribution, what is the lowest number that we have based off of the new distribution? Yeah, so it should be 7. What's the highest value that we have based off of my new distribution? 9. So if you kind of notice, it kind of got more concentrated. So if we're taking a random sample of n many, our new data set should have, well, pretty much it should have a smaller standard error, because the bigger of a sample size we get, the more accurate it should be. So that's what sampling distribution is. So sampling distribution is a process of you get a population and you start randomly selecting from that population. But every time you take a random sample, you take the average of that sample and that count as one data set. So you do that multiple, or not multiple, but you do that several times. And when you do that several times, it creates a new distribution. So let's kind of show that one more. So let's reset this. All right, so let's look at this distribution. What type of distribution is that? Start with a U. Well, for this distribution, if you look at it, since all of them are equally likely, this one is what we call a uniform distribution. So this is a uniform distribution. So what we want to see if it will have the same effect if we take a random sample of n many. Will my new distribution, would it be symmetrical or would it be a normal curve? So let's set this number of sample to 100. We'll do that 30 times. Well, sorry. We'll do a sample size of 30 and we'll do that 100 times. So we'll say draw a sample. So this is my original distribution that we're sampling from. And when we sample from this original distribution 100 times of 30, we get this new distribution. And this new distribution, what type of shape does it have? Yeah, symmetrical. So that's what we're going to be kind of learning today. We're going to be learning about the central limit theorem that just say if we take a sample size of n many, and for the rule of thumb, n has to be greater than or equal to 30. If n is greater than or equal to 30, we could say our data set is normal or approximately normal. All right, so that's what we're going to be doing today. Any questions so far about this? All right. So let's go to the, all right. So these are the two new formula that you're gonna have to learn. Well, one of them, you don't really have to learn that much. So we're gonna say mu of x bar is equal to mu. Because whatever my mean was, the mean should still be the same. So you're saying the mean is not gonna change no matter how big of a sample size we collect. We could collect a sample size of 100, 200, 5,000. Our sample size will still remain our mean will still remain the same. But if you kind of notice, it's saying for standard deviation, our standard deviation is going to change. Because it's saying if we increase our standard deviation should be going down. Because the bigger a sample size you have, the more accurate it should be. So the more accurate it should be, that means standard deviation should be getting smaller because it's getting more accurate. So just to kind of let you know, this one, it has, they usually call this standard error. So if you ever hear me talking about standard error, I'm just referring to that. Right. So those are the two formula you want to know. So you want to know mu of x bar is equal to mu. Sigma of x bar is equal to sigma divided by square root of n. All right. Any question in regard to the two new formulas? All right. So let's get started. All right. So this is the central limit theorem. So the central limit theorem, we only apply if our data set is not normally distributed. Because if I already know my data set is normal, there's no need for the central limit theorem. Because the central limit theorem, we only use it if we want to say something is approximately normal. But if I already know something is normally distributed, there's no need to use the central limit theorem because pretty much I already know if it's normally distributed, whatever sample we take, it should also be normally distributed. So what I'm going to go ahead and do, we're going to just go ahead and look at a couple of pictures to kind of demonstrate that. But the one thing that you do have to know for the central limit theorem, in order for us to say something is approximately normally distributed, our sample size has to be greater than or equal to 30. So if our sample size, say if the sample size that they're randomly selecting is like 5, then for that one, we can't say it's approximately normal because the sample size is too small. But say they say the sample size is 30 or 100. Since 30 and 100 is greater than or equal to 30, now we can say it's approximately normal. Any question in regard to the rule of thumb for the central limit theorem? All right, so let's get into the picture. So if you look at this one, it's a normal distribution. So if we start out with a normal distribution, it doesn't matter how many sample size you take, you're still going to end up with a normal distribution. So if I already know the data set is normal, there's no need for the central limit theorem, because if I already know the data set started off at a normal distribution, I know it's going to end at a normal distribution. All right, so that's for if the data set is normal. All right. If you look at this next one is a uniform distribution, which is not normal. So it's saying if it start off non-normal, it's okay, because if we take a sample size large enough, we could say now the approximately normal. Because if you look at this, if you look at the one at the end, if you look at it, it look approximately normal. So we're gonna say the approximately normal because we took a sample size big enough, which was the 50. So for this one, even though it started off non-normal, we could say it's approximately normal because we know the sample size is bigger than 30, which 50 is bigger than 30. All right, and let's do the last one, I think. So if you look at this one, oops, sorry about that. This one start off non-normal, but since we took a sample size of 50, it actually ended up becoming approximately normal. So this is just going back to the central limit theorem. So the only two that we need to apply the central limit theorem was this one and this one. Because for this one, we start off with a distribution that's non-normal, but since we took a sample size of 50, we know that we ended up with a distribution that is normal because n is greater than or equal to 30. All right. So that's it for the central limit theorem. Any questions so far for the central limit theorem?
What is central limiter?
So the central limit theorem is just a theorem that's telling us, depending on how big of a sample size we're randomly selecting, if our data set will become approximately normal. So the central limit theorem said that if n is greater than or equal to 30, then any data set is approximately normal. It doesn't matter if it's skewed to the left or skewed to the right. It's saying if we start taking a random sample of 30 or higher, it's going to eventually just become approximately normal.
Okay, thank you.
All right, so let's scroll on down and let's do this. All right, let me see. Let me stop sharing. All right, so if you do have the notes, you should have the picture. So you're saying it doesn't matter if our data sets start off as a skew to the right, as a uniform distribution, as a U distribution, or as a left skew distribution. If n is greater than or equal to 30, all of them should end up looking approximately normal. All right, so let's go ahead and do some problem. So let's do the following. All right, so the following problem said describe the sampling distribution of the sample mean. So when I say describe the sampling distribution of the sample mean, I'm asking for three things. So the three things that I'm asking for is for you to say what mu of x bar is equal to, what sigma of x bar is equal to. And lastly, I want you to tell me if the data set is normal, not normal, or approximately normal. So let's go ahead and look at this. So it says describe the sampling distribution of the sample mean for mu is equal to 20, sigma is equal to 12 for a sample size of 9 if the sample comes from a normal distribution. So for this one, let's first do mu of x bar. So mu of x bar is just equal to mu, which they tell us mu is equal to 20. So that's it for mu of x bar. You have to just say mu of x bar is equal to 20. Any question in regard to mu of x bar is equal to 20?
No, because it gives it to us?
Yeah, like since they tell us what mu is, mu is equal to mu of x bar, so you get 20.
Okay.
All right. So let's do sigma of x bar. So sigma of x bar is equal to sigma divided by square root of n. So for this one, sigma is equal to 12. And what is my sample size in this problem?
9.
9. So you put square root of 9. So you go 12 divided by square root of 9, which is 3, gives me 4. And that's your answer for sigma of x bar. Everybody good on how we got sigma of x bar?
Yes.
All right, so up next, what we're gonna go ahead and do, we're gonna try to decipher if this data set is normal, not normal, or approximately normal. So if it's normal, the problem has to tell you the data set is normal. If it's not normal, that means that the data set or the problem doesn't tell you it's normal and it doesn't pass the central limit theorem. If it's approximately normal, that means that the data set wasn't normal, but it passed the central limit theorem. So first thing we're going to look at this problem. Does the problem tell us this data set is normal?
Yes.
Yeah. So since it tells us the problem is normal, we'll say it's normal. And that's it.
So like it's basically trying to like we have to really look into the example question, whether to determine whether it's normal, not normal, or approximately normal.
Correct.
Okay.
But everybody good for part A? All right, let's do part B. So we're gonna do exactly the same thing. We're gonna find mu of x bar. We're gonna find sigma of x bar. We're gonna see if it's normal, if it's not normal, or lastly, if it's approximately normal. All right, so let's get started. Oops. So what's my mu of x bar in this problem? What would it be equal to?
20.
Yeah, 20. So let's put 20. Oops. All right, so let's do sigma of x bar. So sigma of x bar would equal to sigma divided by square root of n. Sigma is still equal to 12, but n in this problem, n is equal to what?
100?
Yeah, 100. So say square root of 100. Everybody good so far on 12 divided by square root of 100? Alrighty. So if you do 12 divided by square root of 100, what do we get for the answer for that one? What's 12 divided by 10? Well, this should give you 1.2. So that's your standard error. So the standard error is 1.2. All right. Any question in regard to standard error is 1.2? Okay, so up next, what we're gonna go ahead and do, we're gonna go ahead and decide if this is a normal distribution, not a normal distribution, or approximately normal. So first thing we're gonna go ahead and do, we're gonna look to see if it's normal. Because if it's normal, the problem has to tell us it's normal. So do the problem tell us that this has a normal distribution?
No.
No. Because if you actually look at it, it said is a skewed distribution. So it's telling us it's not normal. So we know it's not normal. All right. Everybody good why it's not normal?
Mm-hmm.
All right. So up next, we're going to go ahead and decide if it should be not normal or if it should be approximately normal. And this is where you want to apply the central limit theorem. So the central limit theorem says n has to be greater than or equal to 30. In this case, what's my n?
100.
100. So you have to go, is 100 greater than or equal to 30? Well, yeah, 100 is greater than or equal to 30. So since 100 is greater than or equal to 30, your answer will be
Normal.
approximately normal.
Oh, okay.
If our sample size would have been less than 30, then you say the data set is not normal because it's not a big enough sample size. But since n was clearly above 30, that's why we say it's approximately normal. All right, but that's it for B. Any question on how we did B?
No.
All right, so let's do C. So let's see, for C it says, what do you notice? So when I say, what do you notice? I mean, like, what happened when we went from a sample size of 9 to a sample size of 100? So let's see, what happened to mu of x bar? Did it go up? Did it go down? Or did it stay the same? And you can put in the answer in the chat if you want. So what happened to mu of x bar? Like, did it increase? Did it decrease? Or did it just remain the same? Well, if you look at A, for A, what was our mu of x bar?
20.
For B, what was our mu of x bar?
Also 20.
20. So it stayed the same, didn't it? So we'll put same. What about our sigma of x bar? What happened to our sigma of x bar as we increase the sample size? Did it remain the same? Did it increase or did it decrease?
Decrease.
Yeah, decrease. And that's kind of going back to saying like, hey, if I have a bigger sample size, it should be more accurate because if I have a sample size of 100 compared to a sample size of 90, the sample size of 100 should be way more accurate than the sample size of 9. So that's what is reflected. Because if you look at the first one, we have a standard error of 4. But then for part B, we have a standard error of 1.2. So it's becoming way more accurate. All right, but that's it for C. Any question in regard to C? All right, let's scroll on down. So what I want you to do, I want you to try doing exactly what we did right now for this next part. So I want you to find mu of x bar. I want you to find sigma of x bar. And I want you to tell me if this is normal, not normal, or would this be approximately normal? Cool. All right, so take a couple of minutes and try and do that. If you have any question, you could private chat me. For that way I can help you out. Or if you want, you put it in the chat where everybody can see it. Try doing this problem right now.
Professor, the square root of 20 is 4.47, right? Because that's what I got when I used my calculator.
Yeah, it should be something like that.
Okay.
Okay. Okay, so let's try doing this one. So what would be my mu of x bar?
40.
Yeah, 30, perfect. All right, so then sigma of x bar, you should want to do 6 divided by square root of 20. 6 divided by square root of 20, if you do that in your calculator or Cloud Cal, you should get 1.34. All right. Everybody go for that so far?
Mm-hmm.
Okay. So for this one, do they tell me anything about the distribution? Do they tell me
No.
if it's normal, skew? No.
No.
So automatically, he knows not normal. So now what we want to do, we want to see if I could apply the central limit theorem. So to see if I could apply the central limit theorem, I have to see if n is greater than or equal to 30. In this case, if you look at n is what?
20.
Yeah, 20. So 20, is 20 greater than or equal to 30? Well, no, it's not greater than or equal to 30. So that way I could say it's not approximately normal. And we're going to say this is a not normal distribution. And that's it. So in order for it to be non-normal, the problem had to state that the distribution is non-normal and n has to be less than 30. If 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 the distribution is non-normal, then you can't do anything to that problem. So in a test or in a quiz, if you ever run into a problem that's not normal, pretty much you don't have to solve it because it's not solvable. All right, but that's it for that last part. Any question in regard to describing a sampling distribution? Okay, so up next, what we're gonna go ahead and do, we're gonna go ahead and find the probability of a sampling distribution. For this one, there shouldn't be anything new. The only thing new is we have to adjust our standard deviation. But other than that, everything should remain the same. So let's go ahead and look at this next problem. So if you look at this next problem, they tell us mu is equal to 70, sigma is equal to 20, n is equal to 16, and they tell me the distribution is normal. So since the distribution is normal, I could go ahead and find the probability for this. It doesn't matter that n is less than 30, because as long as they tell you it's a normal distribution, you could go ahead and find the probability for this one. All right. Any questions so far on this? Okay, so we're gonna go ahead and do, we're gonna go ahead and find mu of x bar, but we're also gonna find sigma of x bar. So mu of x bar is equal to 70. Sigma of x bar is equal to 20 divided by square root of 16. So if we do 20 divided by square root of 16, we get what?
Five.
Yeah, 5. Thank you. All right. Everybody good? How we got mu of x bar is equal to 70, sigma of x bar is equal to 5. All right. So let's go ahead and find this probability. So if you look at this one, it says find the probability x bar is greater than 67. So this x bar right here, this tell me we're doing sampling distribution. Okay, if you kind of remember before, it was a probability that x is greater than 67. But since they're saying x bar telling me is a sampling distribution. All right. So we're gonna go ahead and find this probability. So first thing I'm gonna go ahead and do, draw it out. So the middle should always be our mean. So our mean in this case is 70. So if you look at it, we want to find the probability x bar is greater than 67. So we're gonna say 67 is to the left of 70 because it's smaller. So we're gonna say 67. Since the inequality is pointing to the right-hand side, you're gonna say the right-hand side. So far, any question in regard to my drawing? Okay, so right now we're gonna do, we're gonna get some information that we're gonna need once we go to class calc, or if you're doing the TI-83. So for the TI-83 or for class calc, it's gonna ask you for these 4 things. So it's gonna ask you what is the mean. So the mean you put is 70. It's also going to ask you for the standard deviation. So for the standard deviation, what you want to do, you want to give it the adjusted standard deviation. So you want to give it this standard deviation. Because remember, we're not doing this for a single x, we're doing it for the x bar. So since we're doing it for x bar, you want to put a standard deviation of x bar, which is 5. So then what we want to do, we want to tell it what the lower bound is. So based off of my drawing, what's the lowest number that I shaded?
7.
Which one?
67.
Yeah, 67, perfect. And then what's the highest number that we shaded?
It's infinity, right?
Yeah, infinity. So you put infinity, if you're doing this with a TI-83 or 84, you want to put 10 to the 10 power. All right. Everybody good so far with those 4 inputs?
What is that thing between the tens? Is that like an arrow that goes up?
Yeah, it's an arrow that point up just to saying that's the power.
Okay.
All right. So I'm gonna first show you how to do this in Class Calc, and then I'm gonna show you how to do it with the TI-83. Because I know there's a couple of you using the TI-83 and 84.
Sorry, have we gone over this already or no?
Well, technically, we have like entering into Class Calc. We have done this before.
Yeah, like we've done this in like a chapter before, or like
Yeah,
in
like
one of
the
the chapters, right?
yeah, we have done this in a chapter before. Like the only thing we're adding is that you have to adjust the standard deviation. So that's the only new thing. Right.
We're on graphing mode, right?
Yeah, always on graphing mode.
Okay.
So what we want to do, we want to hit stats. You want to go distribution/plot. And you want to go right here where it says normal distribution. So under normal distribution, you put mu, which is 70. For sigma, you enter 5. Cool. Then if you want, you could get a picture of it. Then what you want to do is select CDF since you want to find the probability. And for CDF, we'll say that the lower bound is 67, the upper bound is infinity, and we're done. So you get 0.7257.
You said you hit CDF?
Correct. Or press or, yeah. All right. Everybody good on how I did that in Class Calc if you're using Class Calc? Okay, so what I'm gonna do right now, I'm gonna transition over to the TI-83 or 84. For that way, for the people using the TI-83 or 84, they could know how to do that. Okay, so for the TI-8384, what you wanna do, you wanna hit the second button, it's the blue button, the hit second. The reason you know if it's on second, it should become an arrow pointing up, and you hit VARS. So if you click right here, you notice how for number 2 it says normal CDF. You select normal CDF. For the lower bound, you put 67. For the upper bound, you put infinity, but for your calculator, it doesn't have an infinity option. So you put 10. And then if you look right above the division sign, it should be a button that looks like an arrow pointing up. You press that, and then you put 10 again. For mu, you put 70. And for standard deviation, you press 5. And then you go to paste and hit enter. And you should get exactly the same answer that we got in Class Calc. So that's how you deal with the TI-83 or 84. Any question for the TI-83 or 84?
No.
All right, perfect. All right, so we're gonna go ahead and now do part B. So let me switch over back to my notes.
So we just write down the answer as 0.725?
Yeah, 0.7257, and that's your answer. All right. So let's go ahead and let's do B. So for B, pretty much everything's gonna stay the same. The only thing that's changing is my lower bound and upper bound. Okay, if we draw this, the middle should be 70. If you look at it, we want 72. So 72 will be to the right of 70. If you look at the inequality, it's pointing to the left-hand side. So that means we shade the left-hand side. All right. Everybody good so far on the shaded area? All right, so just to kind of save a little bit of time, I'm gonna just copy and paste. All right. So if you kind of look at it, my mu and my sigma are going to remain the same. The only thing that's going to change in this case is my lower bound and upper bound. For this case scenario, what would be my lower bound?
Infinity.
Well, not just any infinity, it has to be negative infinity. But yeah, good. So you put negative infinity, so we put negative 10 to the 10 power. What would be my
Is-
upper bound? What was that, Adam?
Sorry. So negative 10. And what is that sign?
Oh, for this one, are you're using the class calc, correct?
Yeah.
You don't have to worry about this. This is only for people using the TI 83
Oh,
or
okay.
84. But if you're
Oh, so I
using,
don't need that.
so if you're using class calc, pretty much all you have to do is use negative infinity.
I bet. All right. Cool.
What's the upper bound in this case scenario?
72.
Yeah, 72. So we put 72. All right, so what we're gonna go ahead and do, we're gonna go ahead and work this out on class calc. All right, so the good thing about class calc, it already had this information saved about the normal distribution of 70 comma 5. So all I could do, I could press clear and then just re-enter this. So the lower bound, negative infinity, the upper bound is positive 72. So if you do that, you get the answer, and your answer should be 0.6554. And that's it for part B. Any question in regard to how we got the answer for part B?
No, pretty straightforward.
All righty then. Let me change to notes. All right, so what I want you to do, I want you to do part C and I want you to do part D. And what I'm gonna do, I'm gonna open up a poll for part C and D. For that way you can see if you got it correct. So try doing those two right now. All right, so those are your options for part C. So for this first poll, it's gonna be for part C. So once you get your answer, yes, select either A, B, C, or D. All right, so I'll give you 30 more seconds for part C, and then I'm gonna open up a new poll for part D. All right, so we're gonna end this polling. I'm gonna share the results. So if you look at it, everybody almost chose C, and the correct answer is C. All right, so for C, if you didn't get it correct, the lower bound for this one should have been 77. The upper bound should have been positive infinity, or if you have the TI-83, it should be 10 to the 10 power. All right. So I'm gonna relaunch this, and if you already have the answer for part D, just enter the answer for part D. So you either say A, B, C, D, or well, pretty much that's it. So take a minute, do D if you haven't done it. If you have, you have to enter the answer into the poll that you just pulled up.
Shit.
All right, so I'll give you 30 more seconds for D, and then we'll move on. Last 5 seconds. All right, so let me end this. Let me share the result. All right, so if you look at it, mostly everybody chose A, and A was indeed the correct answer. So everybody, good job. So stop share.
I got kind of confused. Like at first, I accidentally put 58 as a lower bound and then UB as like the infinity, but I just noticed that I shaded. Like like I don't know how to explain it, but like
Yeah,
the 58 is supposed to be the lower the upper bound and the lower bound is negative infinity because of the shaded part.
yeah, exactly. So that way I recommend like people doing the shading, because the shading does help you, because it like especially with class calc, if you're using class calc, the good thing about class calc, it give you the drawing. So if your drawing doesn't match up with class calc drawing, then you know something is wrong, because these should be matching up. Like their drawing and your drawing should be pretty identical. All right, but that's it for these last several problems. Any question in regard to any of that? Okay, so up next, we're gonna go ahead and we're gonna go ahead and apply this to a word problem. So let's go ahead and let's go to page number 6, where we'll find a word problem. All right. So for this one, it says suppose the elevator has a maximum capacity of 16 passenger with a total weight of 2,500 pounds. Assume male weight follow a normal distribution with a mean of 182.9 pounds and a standard deviation of 40.8 pounds. All right, so let's go ahead and let's get some information. So the first information that's important, they tell me the mean. I don't want to use that. They first tell me the mean. What do they tell me the mean is equal to?
You scroll down
Like that?
because like you're on the same page still.
I think it stopped sharing the current page that you're on.
Yeah.
Okay. Yeah, I think it froze or something like that. See.
Yeah, that was just me.
Sorry about that.
It's okay.
All right, everybody see that?
Okay, yes, now we do.
All right, cool. Yeah, sorry about that.
It's okay.
So yeah, so for this one, what's the mean weight of a male?
Um, 182.9.
Perfect. So 182.9. What about the standard deviation?
40.8.
40.8. All right. Lastly, for this one, do they tell me what type of distribution do we have?
Normal.
Normal, perfect. All right. Everybody go mu is equal to 182.9, sigma is equal to 40.8, and that this is a normal distribution.
Yes.
All right. So one quick question. How do I know the difference between, so say chapter 14 and chapter 15? So chapter 14, where we're dealing with binomial distribution. Chapter 15, we're dealing with the sampling distribution. So what makes chapter 15 different from chapter 14? Like, how do I know the difference between those two chapters?
I don't know. This one just seems easier.
Well, like for this one, like, because in the test, like I'm gonna give you stuff for binomial, I'm gonna give you stuff for sampling distribution. So like, how do I know that this problem that I'm doing right now is a sampling distribution versus a binomial distribution?
The binomial gives you like the number, and I'm forgetting what else, but the one that we're working on gives you an actual mean.
Yeah, so if you can't remember for a binomial, it'll give me all of this information. It'll give me N and P. But if you look at the sampling distribution, oops. For a sampling distribution, let me see if I could fit this in. It'll give me all of this information. It'll tell me what is the mean, what is the standard deviation. So thank you, Nami. So that's how you know the difference between chapter 15 and chapter 14. So that way during a test, you should be looking for that to kind of distinguish, is this a binomial distribution or is this a sampling distribution? All right, everybody kind of good with that? All right, so let's do part A. So for part A, it says, for this problem, do we need to apply the central limit theorem? So if I already know this data set or this distribution is normal, do I need the central limit theorem?
No.
No.
They say more confident. Yeah, no. Because you go, no, we don't need so for the central limit theorem, when you put CLT, you have to make this a little bit shorter. So we say, no, we don't need the central limit theorem since we already know the distribution is normal. So once you know the distribution is normal, there's no need for the central limit theorem. All right, and that's it for part A. So for part A, everybody go for part A?
Yes.
Okay, let's do part B. So for part B, it says find the probability that one randomly selected male has a weight greater than 156.25 pounds. All right. So for this one, how many male are we randomly selecting?
One.
Perfect. One. So for this one, it's like the problem that we used to do when we had one random selection. So when we have one random selection, you're going to use mean is equal to, well, the mean, which is 182.9. Since we only have one random sample, you keep your standard deviation at 40.8. So when n is equal to 1, you don't do anything to the mean or to the standard deviation. They stay the same.
Wait, where does 40 point? Oh, wait, never mind. Yeah.
40.8 is from here, or if you look right here, it's right. All right. Everybody get why we still use mean and standard deviation, or why doesn't it change? All right. So let's go ahead and draw this out. So the middle will be the mean. So we'll put 182.9. If you look at it, this is 156.25. So that's somewhere to the left of it. And which side should I shade? Should I shade the left side or should I shade the right side?
The right side.
Yeah, good. Thank you, Anna.
Because it says greater than, right?
Perfect, because it says greater than. All right, so for this one, what will be my lower bound and what will be my upper bound? So let's do lower bound. What will be my lower bound? So what's the lowest value I have shaded?
156.25.
Yeah, cool. Thank you, Naomi. What about my upper bound? What would be the highest value that I should shade?
Infinity.
Infinity. So you put infinity or 10 to the 10 power. Everybody good so far on lower bound and upper bound? All right, so I'm going to do this one using the TI-83. So we'll say on. So we'll go second and then go VARS. You do normal distribution. We'll put lower. Lower bound is 156.25. My upper is 10. I already had it. To the 10 power. And then my mean will be 182.9. My standard deviation will be 40.8. If you're doing this in class calc, you do the normal distribution, put the mean, put the standard deviation, you should be fine. And for this one, you should get the answer of you should get the answer of 0.7432. And that's it for part B. Any question in regard to part B? All right, so let's do part C. So now I'm going to switch over back to the notes. All right, so hopefully everybody should be able to see the notes right now. So for part C, it says, assuming a worst case scenario in which the passenger are all male, what are the chances the elevator is overloaded? Find the probability that a sample of 16 male have a mean weight greater than 156.25. So for this one, they changed the n for us. So for this one, what is our n value?
16?
Yeah, 16. So now my mean, well, the mean is still 182.9, but my standard deviation, now we have to adjust it because now we're doing it for a sample of 16. So what we want to do 40.8 and we want to divide this by square root of 16. If you actually go ahead and do that math, you should get 10.2. So instead of putting standard deviation of 40.8, like we did for part B, we have to adjust it and put that the standard deviation is 10.2. Any question in regard to why we're adjusting the standard deviation? And if you look at the drawing should be the same. So I'm gonna go ahead and recycle this drawing and put it again. If you look at this one, the lower bound, the upper bound will be the same because we still want to find the probability is greater than 156.25. So I'll say 156.25, and we'll put upper bound is positive infinity, or if you're using the TI-83 or 84, you put 10 to the 10 power. All right. Any questions for the difference? Well, any question for part C?
Yeah. If this was like a question on a test, like what would you be asking?
Well, it will pretty much be the same way I'm asking right here to find the probability that the sample of 16 male have a mean weight greater than 156.25. So I'll just ask it like I asked it in this problem. Does that kind of make sense, Anna? Or were you
Yeah.
asking something differently?
No, yeah, no, that makes sense.
Okay. All right. So what I'm going to go ahead and do, I'm going to go ahead and now do this in class calc. So in class calc, I'm going to go, you can actually just adjust it. So I could put 10.2. For the mean, we could put 182.9. And then for my lower bound will put 156.25. And then for this upper bound, you put infinity. So if you look, you should get 0.9955.
0.9955. Okay.
All right. Everybody was able to get that?
Yes.
Mhm.
All right, so we're almost done with this problem. We have to do part D and then we'll call it a day. So we get 0.9955 for our answer. So the last step we're gonna do part D. We say which probability is greater. Well, there's a typo. That should say part B. That should say part C. So which probability is greater, part B or part C? That's a good question.
Part C.
Yeah, part C. All right, and we're done.
Yay.
So that's it for today. So I'm gonna have office hour like 5 minutes from right now. So if you have any question